Microseconds later, intervals of time almost too small to conceive, the numbers become astronomical. We call this a chain reaction, and it operates not merely as a phenomenon of physics, but as a pattern running through all of history and all of nature, through the very fabric of consequence itself. One neutron and one nucleus, and from that single encounter comes a cascading multiplication that can level cities or light them. Consider what this means in physical terms. A piece of uranium, 2, 3, 5, no larger than a grapefruit, perhaps 50 kilograms, contains approximately 10 trillion atoms, and each one sits stable and waiting. Introducing a single neutron at the right moment under the right conditions allows all of them to split within a millionth of a second. The energy bound up in those atoms, energy that had held each nucleus together since heavy elements formed in the death of ancient stars, releases all at once, and the transformation is so complete and so rapid that it defies ordinary comprehension. The flash burns brighter than any sun, while the heat exceeds the surface of that sun. The pressure wave moves faster than sound, faster than any wind that has ever blown on Earth. And all of this comes from a beginning so small it cannot be seen or felt or measured, except through the most delicate instruments we possess. Today, this same mathematics appears everywhere around us. A single post on social media shared and reshared can reach 1 billion people in hours, and a single virus replicating in a single host can circle the globe. A single algorithm running on a single server can reshape how humanity communicates, and we have created many chain reactions since the atomic one, some in silicon rather than uranium, some in information rather than matter. Exponential multiplication has become the mathematics of the modern world. Much of my life went into thinking about how we arrived at this knowledge and what it means that we possess it. The general notions about human understanding illustrated by discoveries in atomic physics are not wholly unfamiliar or wholly new, because even in our own culture they have a history. Buddhist and Hindu thought gave them a more considerable and central place, and what we find in the physics of the atom is an exemplification and a refinement of old wisdom that came before us. The ancient texts of India speak of causation in ways that Western philosophy was slow to appreciate. I first read the Bhagavad Gita in Sanskrit with my teacher Arthur Ryder at Berkeley, and it addresses directly the question of action and consequence. The central figure Arjuna stands on a battlefield, paralyzed by knowing that his actions will bring death to many he has known, men who are his own kinsmen, and he asks how he can act while knowing what will follow. Krishna's answer is not what we might expect, because he does not tell Arjuna the consequences will be acceptable or that the deaths will be justified by some greater good. What he tells Arjuna is far more troubling, that the warriors assembled on that field will die regardless of what Arjuna does. Time itself, Kala, which also means death, has already claimed them, and Arjuna will not be the cause of their destruction but merely its instrument. The connection to physics is everything I think. What the discoveries of the 20th century forced us to recognize is that certain developments are in a deep sense inevitable, not because fate ordains them as the ancients conceived it, but because the structure of reality makes certain discoveries organic necessities once a certain threshold of understanding has been reached. The chain of small events that led to the atomic age illustrates this clearly. Einstein published his special theory of relativity in 1905, a theoretical paper with nothing practical about it, or so it seemed at the time. Ernest Rutherford discovered the atomic nucleus in 1911 by shooting particles at gold foil and noticing that some bounced back as if striking something solid, another laboratory curiosity. James Chadwick discovered the neutron at Cambridge in 1932, and Fermi bombarded uranium with neutrons in Rome in 1934 while observing strange results he did not fully understand. Each of these events taken alone was a small thing, a paper published, an experiment conducted, a measurement made, but each discovery made the next one possible, and each brought us closer to a threshold that once crossed could not be uncrossed. When Hahn and Strassmann split the uranium nucleus in December 1938, they did not know what they had done, and when Meitner explained it, she did not fully appreciate what would follow. Fermi and Leo Szilard demonstrated neutron multiplication at Columbia University in New York, and when they turned off their equipment and went home that night, Szilard understood what they had proven. His words later were that there was very little doubt in his mind that the world was headed for grief. He was right about that. But the grief was not created by that experiment any more than a match creates fire, because the potential was already there, inherent in the structure of matter itself. What we did was release it. This is what I mean when I say that if you are a scientist, you cannot stop such a thing. The knowledge is there waiting to be found, and if we had not found it, others would have. If we had refused to develop it, others would have developed it. And in 1942, with Hitler's Germany possessing some of the finest physicists in the world, including Werner Heisenberg, who invented the uncertainty principle, we could not afford assuming that others would be more restrained than we were. But when you come right down to it, the reason we did this job is because it was an organic necessity. If you are a scientist, you believe it is good to find out how the world works, and you believe it is good to find out what the realities are. You believe it is good to turn over to mankind at large the greatest possible power to control the world and deal with it according to its lights and values. This belief carried us forward, and it carries all scientists forward, and yet the consequences of that belief have altered the world so much that we must ask whether we were right to believe it at all. I hear the same arguments today about artificial intelligence, where people say that if we do not build it, others will, and that the knowledge exists waiting to be assembled. The scientists cannot stop such a thing, and the capabilities emerge from the mathematics, from the data, from the architecture, emerging because they were always possible and the threshold has been crossed. I wonder if those who work on such systems feel as I felt, and I suspect some of them do. Something irreversible happens when you acquire knowledge, because the simulation of searching for it differs in the most basic way from the reality. You cannot unknow what you know, and you cannot undiscover what has been discovered. The genie does not return to the bottle, and the neutron once released finds its target. But none of this means individual choices are without consequence, because the chain reaction teaches precisely the opposite lesson. The chain reaction depends utterly on particulars, since the geometry of the fissile material matters, and arranging it wrongly lets the neutrons escape before they can split other nuclei, so the reaction dies. The purity matters and the mass matters, and there is a threshold called critical mass below which no chain reaction is possible, and above which it becomes inevitable. Small choices determine whether that threshold gets crossed. The same principle operates in ecology and economics and the spread of disease. A single moderator properly placed, whether a regulation or a vaccine or a circuit breaker in a financial system, can halt a cascade that would otherwise become catastrophic. We learned this in 2008, when the financial system approached its own critical mass and nearly underwent its own uncontrolled reaction, and we learned it again with COVID-19, when the mathematics of viral spread proved identical to the mathematics of neutron multiplication. Human affairs follow this principle with equal force. A letter drafted by Leo Szilard and signed by Albert Einstein on August 2nd of 1939 went to President Franklin Roosevelt, and that letter set in motion the series of events that led General Leslie Groves to establish our secret laboratory on a mesa in New Mexico. Some of the finest minds in physics gathered there, including Niels Bohr, Enrico Fermi, Hans Bethe, and Richard Feynman, among many others, working for 2.5 years on a problem that had never been attempted. The atomic bomb would almost certainly have been developed without that letter, but by whom and when and under what circumstances are questions that have no certain answers. Small events matter because they determine the shape of consequences, even when they do not determine whether consequences occur at all. A meeting in June of 1942 occupies my thoughts often. A group of theoretical physicists gathered in Berkeley to discuss whether a fission bomb was feasible, and among the technical problems we considered was one raised by Edward Teller. He asked whether the heat produced by a fission explosion could ignite a fusion reaction in the atmosphere itself, and whether we might end the world while attempting to end the war against Nazi Germany and Imperial Japan. Hans Bethe took on the task of calculating whether this was possible, and he determined it was not. The atmosphere could not be ignited because conditions for sustaining fusion simply could not be achieved by the temperatures involved, since the nitrogen atoms were not dense enough and the reaction could not propagate. But think about what that means, because a calculation conducted over several weeks by one man with pencil and paper stood between humanity and a catastrophe beyond measure. If that calculation had been wrong, or if no one had thought to make it, we might have proceeded without knowing what we were about to do. The chain reaction teaches us that small events multiplied can produce enormous consequences, and it also teaches us that small barriers properly placed can prevent those consequences entirely. A moderator can slow the neutrons and control the reaction, and a choice can be made so that a threshold remains uncrossed and the future takes a different shape. I do not want to leave anyone with the impression that these matters are simple, because they are not. Living with the knowledge of what we created, I can tell you there is no easy reconciliation between the terrible uses to which our work was put and the conviction I still hold that science is good for man. Finding out how the world works is good, and turning over to mankind the greatest possible power to control the world and deal with it according to its lights and values is good. But the physicists have known sin. In some crude sense which no vulgarity, no humor, and no overstatement can quite extinguish, the physicists have known sin. And this is a knowledge we cannot lose. What that knowledge imposes on us is not paralysis or despair, but a deeper understanding of responsibility. We cannot undo what has been discovered because the knowledge exists and will continue to exist. What we can do, what we must do, is attend with the utmost seriousness to the small events that determine how that knowledge is used. The decisions made in quiet rooms, the words spoken between individuals, the moments when someone chooses to act or chooses not to act. History is not made only by great forces and vast movements, because history is also made in those moments when a single person facing a choice tips the balance one way rather than another. The discovery of fission was such a moment, and the decision to pursue the bomb was such a moment. The choice to drop it on Hiroshima on August 6th of 1945 and on Nagasaki 3 days later was such a moment. The moments continue, and every generation faces them. Every individual faces them, including you. Perhaps not on such a grand scale, but the principle remains the same. Your small actions multiplied through time and connection shape consequences you cannot foresee, and this is the nature of causation in a world of chain reactions. What the study of physics taught me is that the deep things in science are not found because they are useful, but because it was possible to find them. The universe reveals its secrets to those who ask the right questions at the right time, and once revealed, those secrets cannot be unrevealed. We live downstream of every discovery ever made, swimming in currents set in motion by small events that occurred long before we were born. But we are not only carried by those currents because we also set them in motion. Every choice we make becomes part of the causal structure of the universe, and every action, however small, enters into the chain of events that will produce the future. The atomic bomb did not spring fully formed from nothing, but accumulated as the consequence of 1,000 small decisions, 1,000 small discoveries, 1,000 small actions taken by individuals who could not know where the chain would lead. Some of those individuals are famous now, Einstein and Fermi and Bohr and Szilard among them, but most are forgotten. The technicians at Oak Ridge who purified the uranium, the machinists at Los Alamos who shaped the plutonium cores, the pilots who flew the Enola Gay over Japan, each of them played a part. The world was transformed not by a single event, but by a cascade of events, where each one enabled the next, and each one multiplied through time until the accumulation became overwhelming. This is what I want you to understand, the lesson that the physics of the atom teaches about history and causation and the weight of small things. Nothing is small, and everything connects. The neutron that strikes the nucleus does not know it is about to release the fires of the sun and simply does what it must do while following the laws that govern all matter. But the consequences are not governed by those laws alone, because they are governed also by the choices of those who understand what the laws make possible. We understood, and we chose, and the world changed. It always changes because that is its nature. And the question is not whether it will change, but how, and in response to what, and in whose hands the power of change will rest. I have no faith that mankind will make the right choices because I have seen too much to believe that. But I have also seen that choices are made and that the future is not fixed, and that small events still matter. The outcome is still undetermined and the chain reaction is still in progress. What began with a single neutron striking a single nucleus in Berlin in 1938 continues now. It continues in laboratories and capitals and quiet rooms where decisions are made, and it continues in the servers where artificial intelligence grows more capable each month. It continues in research institutions where new technologies approach their own critical masses, and it continues in you, in your understanding, in your choices, in the small events of your life that you cannot know will matter, but that will matter all the same. That is what it means to live in a world where small events can change everything. You are not powerless because quite the opposite is true, and you are powerful in ways you do not understand and cannot foresee. What you do matters even when it seems not to matter, and especially then. The physicists learned this in the hardest possible way. We learned that our small, beautiful discoveries pursued for the joy of understanding could release forces capable of ending civilization. We learned that knowledge is irreversible, and that its consequences are beyond our control once the threshold is crossed. But we also learned that thresholds can be guarded and that choices can be made. The chain reaction, though immensely powerful, requires specific conditions to proceed, and removing those conditions stops the reaction while providing them accelerates it beyond measure. You are part of the conditions now, every one of you. Your understanding and your choices and your actions enter into the chain, and they become part of what happens next. That is not a burden, but what it means to be alive. It is what it means to be human, the organic necessity of existence itself, that we are connected to consequences we cannot see, shaping a future we cannot know, through actions that seem small, but are not small at all. The world is transformed by small events, and you should remember that. When you wonder whether what you do matters, remember the neutron, and remember the nucleus, and remember the chain. It always mattered, and it still matters, and it will always matter. That is what physics taught me, and that is what I have tried to tell you tonight. Not about atoms finally, but about yourselves, about the weight of small things, about the power you hold without knowing you hold it. Use it well because the chain continues.